Okay, in this video we're going to explore the idea of reflection, and we're going to start by looking at the law of reflection. Now, the law of reflection is maybe the simplest physical principle that you will ever see in this class, and the statement of the law of reflection is simply that the angle of reflection is equal to the incoming angle. Now, oftentimes in physics we don't usually refer to the incoming rays of light as incoming. Usually the word that is used is incident. So you may hear me go back and forth between those two. But ultimately, the law of reflection is pretty simple. It says that the angle of reflection is equal to the angle of incidence. So unlike Snell's law, which is kind of a complex trigonometric function, this one is very simple. This angle equals this one. There's really no math that even could be done with this law of reflection. Let's take a look at what it physically looks like. So imagine that we have a very flat and smooth surface, and that some ray of light is traveling in and strikes that surface. Okay, now just like we did with refraction, we're going to think about the angle in terms of its relationship to the normal line. The normal line is that line which is perpendicular to the surface. So here on the left side is the incoming photon of light, and then on the other side we're going to have a ray of light, that same ray of light traveling outward, and that would be our reflected angle. Okay, so these two angles are equal to each other. And I feel like that's probably in your experience, that it makes sense that these two angles are equal to each other. Very simple relationship. But this leads to kind of a tricky thing when you think about, well, what will you see? When you see this ray of light come to your eye, what will you see? Are you going to see like an image of something that was over here? Or are you just simply going to see this surface? And we see both. And those refer to two different types of reflections. So let's take a look at those. The first one is called specular, and the other type is called diffuse. So let's take a look at how specular reflection works. Okay, in specular reflection, instead of drawing a single ray of light, let me draw several rays of light, and let's imagine that these rays of light have traveled to this surface after they bounced off of a tree. So the tree, which is far away, has had rays of light that bounced off, and by the time those rays of light reach all the way over here to this very shiny surface, the only rays that really remain that strike this surface traveled in a nearly parallel path from the tree. Now when they strike the surface, they will be reflected following the law of reflection, and because they were all parallel to begin with in the first place, they will continue to travel parallel to each other. So the meaning of that is that the image will be retained. So if I were over here looking, I would see the image of that tree over there. It would appear when I looked at this surface, I could see the tree on it, even though the tree is over here. So because the rays of light stayed parallel to each other, they also went out parallel to each other as they bounced off this identical surface. And the word for that is coherent. The light is coherent. So as long as the light remains coherent, you should see the image of whatever that light came from. If it was from a light or from something, it bounced off of something, you should be able to see the coherent image. Now, on the other hand, in diffuse reflection, what we're looking at is an irregular surface. If you could see the surface of most objects, you would see that they are actually not very smooth at all. Even objects like glass that might appear to be very smooth is not actually that smooth. But certainly most other surfaces, like imagine light that bounces off of your clothes. Well, that's a very, very irregular surface. So let's imagine the four photons of light coming in, just like we did before. These came into the surface, and when they came into the surface, they were coherent. Okay, so as you can imagine, the rays of light here will bounce following the law of reflection. They will follow the same angle that they came in, but because the surfaces here are now tilted in all different directions, they are going to bounce out in different ways. So the effect of the diffuse reflection is that the light is scattered. So now the light doesn't contain any information about the image, because one photon or one ray of light is not enough for you to see an image of something. That's just one little tiny part of the tree that it bounced off of. Now you can imagine other light coming in and striking these surfaces and going out in this direction. Or maybe light came in from this direction and bounced and came off in this direction. So this will not be the only photon of light that's going to travel in this direction, but the problem is that the other photons of light that are going to travel in this direction, they came from all over the place. They came from above, they came over here from the right, they came over here from the far left and bounced off into the direction that your eye was at. And so as a result, you don't see the image. What you see is this surface. You see whatever photons bounced off this surface. It allows you to physically see that there is an object there, that the object is in the direction that if you follow those rays of light back to the surface, that's what you're going to see. And it's simply going to be a reflection of whatever this surface was, whatever color the surface was, that's what you're going to see. But you will not see the image that the photons of light originally came from. You'll just simply see the surface of this object. So that's specular and diffuse. These would be called non-coherent. So the light is no longer coherent. It came in coherent, but it doesn't go out coherent because of the irregularity of the surface. Now let's take a look at another aspect of this, which has nothing to do with the angle that it came in with, but simply what kind of boundary did the ray did the wave run into. So we're going to look at two types of boundaries. There is one type of boundary in which the medium is fixed to something, and then there's other cases where the medium is not fixed. Those are referred to as open. So in order to do that, what I'm going to do is I'm going to draw a solid wall over here. And I'm going to bring in a pulse. Okay, now just to make sure that it's easy to keep track of the left and the right side, I'm going to purposely not make the pulse symmetric. So let's say that we had a pulse that looked like this. Okay, now what I'm trying to indicate to you here with this, the way that this is drawn, is that this is a solid wall and that this is physically connected. It's tied to the wall. So this point right here cannot move. Every other point on the string can move, either up or down, but not this point right here. So what is going to happen when this pulse reaches the wall? Okay, well, what's going to happen is that this portion of the string is displaced in the upward direction. So when it arrives here, remember, this is how waves travel in the first place. The wave pulls up on the string. Okay, that little piece of string or that little piece of the medium pulls on the guy next to him, and that pulls on the guy next to him, next to him, next to him, and then the wave continues to travel down the line. So as this portion of the wave arrives here at the wall, it is going to begin to exert an upward force on the wall. Okay, the string will exert an upward force on the wall. So therefore, what is the wall going to do? Well, according to the third law, if a force is exerted on the wall will always exert an equal but opposite force on the thing that exerted that. So in this case, it's the string. So the string exerts a force on the wall in the upward direction. The wall exerts a force on the string in the downward direction. So the pulse, when it reflects, it is going to come back off of this thing, but when it comes back, there's going to be two things you're going to notice about it. So first of all, it's going to be flipped upside down. So our incoming wave was coming this way, this guy was still traveling in that direction, but now the wave is traveling outward in this direction. So if you notice one thing, when I looked at the image over here, I saw the tall side was on the right, but now the tall side is on the left. And that is because that's the first thing that reflected. The first thing to reflect. So if you can imagine the wave coming in like this, as it reflects, it starts bending backwards. So the first thing to get reflected is that leading edge. So that leading edge gets reflected first, and that's going to flip the guy backwards. So left to right, it's backwards. But also, because the force that was exerted on the string was in the opposite direction of the original pulse, the pulse comes back upside down. So this is what happens on a fixed boundary. You end up with the pulse reversed and also flipped upside down. Now let's take a look at what happens to the open boundary. Now to create an open boundary, what we're going to do is we're going to imagine a ring connected to a rod, a metal rod. And the string is now connected to it, and I'm going to use the same pulse. Okay, so the pulse is traveling in this direction. Okay, so what's going to happen in this situation is that because that rod, and we're going to say that this is frictionless, this is really important, and the reason I want it to be frictionless is I don't want the rod to be able to exert any force on the string other than the tension in the string. So I want this ring to be able to slide up and down without any friction at all, so that there will be no force exerted by the rod on the ring. So as a result, when we get here and the pulse arrives here, that ring is going to move up. The ring is going to move up. Now, because the ring moved up, as soon as the ring begins to move up, it begins to exert a force back on the string. But because the ring is moving in the upward direction, it exerts an upward force on the string. So when the pulse goes back, the pulse will be flipped because look, the taller end hit first. So that's the first part that's going to be reflected. So it is going to be turned backwards compared to the original wave, but it will not be flipped upside down, because by taking away the ability of the rod to exert any force on the string, I've taken away the third law aspect of it. So there is no way for the rod to exert a force back onto the string. And as a result of the fact that the rod moved in the upward direction, when it moved in the upward direction, it exerted a force on the string in the upward direction. And therefore, when the pulse comes back, it comes back on the same side. And that's something that we can demonstrate in class. It's very easy to demonstrate this in class. It's not quite as easy because it's really hard to create that frictionless surface. Sorry, I forgot to put the ring here. To create that frictionless surface for the open boundary. But ultimately, in any open boundary, you would see that the wave comes back exactly as it was. But of course, it's flipped around. In the previous example, when we looked at the law of reflection, we were talking about rays of light. Now, rays of light are not connected to anything, so therefore they are always open boundaries. So they always come back on the same side that they originally reflected. They don't get flipped upside down. But on the other hand, string connected to a surface where it is not allowed to move, that is going to cause the reflection to flip upside down. That might seem like, well, where would that happen? In a guitar. A guitar would be a perfect example where the strings are tied at the ends, they are connected, so that when you produce a wave on a string, it goes down to the end and then flips upside down and comes back in the other direction. That's a big part. It's a kind of an important part of how musical instruments work, and particularly strings, is this idea of the way that they reflect. So when you pull on the string, the wave starts going back and forth between the two endpoints, and every time it hits the other end, it flips upside down and travels back, and then flips over and comes back. And then we'll get into that when we start talking a little bit more about musical instruments.